we're now getting to future-proofing ontologies, which will involve some details to illustrate what I claimed earlier, which is that the gene ontology found a way of moving to a higher level in such a way as to expand the degree to which the gene ontology would prove to be beneficial, not just for one specific application, but over a whole series of applications, which is still continuing after 17 years, 19 years. So this is a picture of the very first OBO Foundry conception. And you can see that the gene ontology, which is marked in yellow, is now just one part of a larger edifice. And the way in which this picture is organized, which is very much influenced by the way in which the gene ontology is organized, is as follows. Along the vertical axis, you go from very small things, such as molecules, to larger and larger things, such as whole organ. And in fact, we'll go larger still as time goes by. And from left to right, you have an organization in terms of the kinds of entities that we're dealing with. So the first column is things, which we call independent continuants. They're continuants because they continue to exist. An organism continues to exist for the whole of its life. And they're called independent because they are self-standing. They don't need anything else in order to exist, in the way in which dependent continuants, such as functions or qualities, are not self-standing. And then biological processes form a third column, which is the column where we put what we call occurrence, which are things which do not continue to exist, but rather occur. They exist by occurring. So your life is a continuant. Your life is an occurrence. It has a beginning, a middle, and an end. You are a continuant. You don't have a beginning and a middle and an end. You have body part. Now, in around about 2005, we added the environment ontology, which will be very important for our study of definitions of system later in this collection of talks. So the environment ontology crosses granularities. We have molecular environments, cellular environments, and then, of course, environments, habitats for organisms. And at around the same time, we expanded also to include not just natural biological processes such as cell division or death, but also protocol-driven processes called experiments or studies or trials or investigations. And we invented an ontology called OB, which contains terms that we use to describe experiments. And the reason for this is that you can't really understand a gene sequence, for instance, or a gene array, unless you know what steps were taken to derive that sequence. And so we need a controlled vocabulary for describing how particular kinds of products of scientific experimentation are being created, which will contain words for things like protocols, equipment, settings, inputs, outputs, gels, stains, observations, and so on and so on. And then, as a result of building OB, we realized that we needed words like publication and footnote and author. And it occurred to us that it's a bit unusual to suppose that the word author is tied closely to biological experiment. Surely, we said, there is a more general ontology, which would be an ontology for information artifacts in general, independently of whether they're biology or physics or journalism or software. And so we created IAO, the Information Artifact Ontology, which is an ontology of things like data, ontologies, publications, and all of those things. Law, in the sense of written law, imaging, and so forth. So IAO is a kind of, it's the mother of OB, which it was born after OB was born. And then there is a big link between IAO and OB on the one hand and all the other ontologies, which is that the terms in IAO and OB are in some sense about these other terms. So experiments are about cells or molecules or organisms. Publications are about organisms or events or whatever. Right? All right, so future-proofing means rising to a higher level of generality. And then the question arises, so you're going to make sure your ontology is future-proof. You rise to a next level of generality, but then when you get there, you say, well, maybe I need to go to another level of generality. And that process can't go on forever. There has to be a top level of generality. And this follows also from the strategy for writing definitions. There has to be some term which is not the child of another term, because otherwise definitions would go infinitely onwards. And already Aristotle recognized that there had to be what he called categories, which are not standing to anything higher in the way that the species stands to a genus. So he wrote a whole book called Categories, which was the first ontology. And this is the way in which Porphyry, who was a commentator on Aristotle, may have drawn a picture. So he gives us the ingredients for this picture. And the supreme genus, he says, is substance. And then there are material substances called bodies. There are living things which are animate bodies. There are animals which are sensitive living things. And there are humans which are rational animals. And then there are instances of human, such as Socrates. Now that means that we need to understand, if we're going to do ontology properly, what goes at the very top. And of course, even Aristotle saw that there were other things at the very top. In addition to substance, there are things like quality, placing, which are not substance. And the Go has these three ontologies. Each has something at the top. But the something at the top is only top in a biological context. It's not top absolutely, as is seen by the fact that we can recognize that biological processes are processes. And that's higher because there are other processes which are not biological. So these are the root nodes in the Go, and we created BFO by a process of reverse engineering the Go, by taking the Go's three distinctions and making them absolute. This is a top-level ontology of category. And so the three categories are independent continuous, dependent continuous, and current. And now I have another handout. So don't try and read that diagram all in one go. You will hear bits of it as we go along. So independent continuants are things like objects such as you and parts of objects such as your head or your finger. Dependent continuants are things like attributes, roles, functions. We'll talk about those later on. And then occurrence are processes, including things like missions and operation. And now, if we think about independent continuants in the realm of systems engineering, then we would have things like systems themselves, but also system designers, system operators, system managers, and so forth. And occurrence would be things like building, maintaining, operating a system. So it's important to realize the division between continuance and occurrence. Occurrence are processes. They take time. They have beginnings, middles, and ends. And that's, as I said earlier, the rationale for this OBO Foundry organization. And there is a book called Building Ontologies with Basic Formal Ontology, which describes how to build ontologies using basic formal ontology. And it's the only book in the world with the word ontology twice in its title. So BFO is very small, as you could imagine, because it's completely general. It applies to everything in the universe. Because it's very small and because it has so many people who use it, it changes slowly. So we have only had 3 versions: version 1, version 1.1, and now version 2. Version 1.1 consisted in adding information artifacts, or anyway, the corresponding parent term for information artifacts, which we realized we didn't have in version 1. And version 2 consisted in cleaning up various things. All right. Now, it's strictly formal, not in the sense of formal logic, but in the sense of formal versus material. It doesn't have any specific matter which it pays attention to. It's completely domain neutral. So just as the gene ontology is species neutral, so BFO is domain neutral. It works for astronomy as well as it works for philately or coin collect. It has a lot of people who are using it and a lot of people who are helping to maintain it, some of whom are very critical, painfully critical. And it has a cadre now of people who know how to build ontologies using BFO, who can help you populate your ontology so that it works well with the ontologies which already exist. And so I like to think of ontologies as being like telephone networks. Some of the ontologies built using BFO are not great. They are either because they're young or because they have had too little work invested in them, or because they deal with difficult terrain. But they are ontologies which work with other ontologies. They communicate. There is a certain degree of interoperability. Now, if you have a telephone network with no customers, but absolutely fantastic wiring and equipment and so on, you have nothing. If you have a telephone network with 4 million subscribers, you have everything. Now, BFO-based ontologies, they probably don't have 4 million subscribers, but they said that it will go through in this year. It will be ISO number 21838-2. -1 is the standard for being a top-level ontology, and -2 is the demonstration that BFO satisfies the requirements of that standard. And this is just a few examples of ontologies which are using BFO, and you can find the whole list here. This is public domain ontologies. There are some non-public ontologies which use BFOs also. And now I'll talk a little bit about the Industry Ontologies Foundry. This was created in 2016 by a group of people around NIST to create for industry what the OBO Foundry had created for the biology world. So the goal was to create, again, an interoperable suite of reference ontologies covering initially manufacturing. And there are various government bodies involved. The Air Force Research Lab is the most important one alongside NIST. And we have various potential collaborators. So we're still hoping that the Jet Propulsion Lab will build its ontology within the OBO Foundry framework. We also have the European Materials Modeling Council, which has an ontology, which I will talk about very soon, which we also hope will become part of the OBO Foundry. And then we have various industry collaborators, and these are just some examples, including Kubrick. I guess that's industry in Buffalo. And we have various academic organizations which are also participating in the OBO Foundry effort. And one participant, it's not part of the OBO Foundry because the OBO Foundry doesn't have parts yet. It's still very much in the beginning phase of organization. But it provides a model for the way in which the OBO Foundry might look. So the Common Core ontologies are a suite of ontologies developed to support various military efforts primarily, although it's more generic than that. So we have an agent ontology, a quality ontology, an event ontology, an artifact ontology. under the artifact ontology, we might then extend to create a military vehicle ontology or a space vehicle ontology. And we have done some of that. And you see that the whole thing is based on BFO. And we have the information entity ontology on the mid-level. And here are some of the extension ontologies. So we have a space object ontology, a units of measure ontology, a sensor ontology, an undersea warfare ontology, and so. And now this would be another way of viewing the Common Core ontologies, and then we could view the OBO Foundry, the industry ontologies, rather like this. So this is just a first effort to predict how the OBO Foundry will develop. And then we can combine the Common Core ontologies with the OBO Foundry ontologies and see how they are connected, or how they might be connected, in that the ones down here would extend the ones up here. And the four materials ontologies that you see there already exist. And they're all BFO based, or they are being re-engineered to be BFO based. CHEBI is a chemistry ontology, which is a very large ontology. The product lifecycle ontology I will talk about in the afternoon. All right, so one area where we are most developed in the industry ontologies foundry work is the materials ontology. This is because the Air Force Research Lab has been doing a lot of work on materials science ontology, which we can now exploit. There is what we are using the term mat-onto to designate a suite of ontologies based on BFO to cover different kinds of materials. And these are kinds of materials for which we already have the starting point. And the European materials modeling ontology is attempting to create an ontology not so much of materials as of materials models. And you need to bear that in mind. I'm going to present this ontology. It is based on BFO. It goes into great detail about specific kinds of distinctions among material models, which I will merely hint at as I go through some of these slides. I'll start by showing you how BFO deals with materials. First of all, if I say I'm interested in sugar, or I'm interested in oxygen, then that can mean two things. It can mean I like eating sugar, or in other words, I'm interested in specific lumps of sugar or packets of sugar or spoonfuls of sugar on the one hand, or it could mean I'm interested in the chemistry of sugar or the physics of sugar. And that means I'm using the word sugar in two different ways. On the one hand, I'm using the word sugar to refer to portions of sugar, which are real bits of material that I can have in my hand. But in the second way, I'm using it to refer to the kind, sugar. Now, how can I describe? They are two different words. And one way in which ontologists who've attempted to study materials, and indeed other things, have made mistakes in the past is they haven't realized that those are two different meanings. So they've confused sugar as a kind of material with sugar as portions of material. Now, BFO avoids this problem by never using mass nouns. And mass nouns are nouns like sugar or luggage or information or discourse or knowledge that don't have plurals. You can't count knowledge. You can't count discourse. You can't count oxygen. You can count molecules of oxygen. You can count tubes containing oxygen, but you can't count oxygen. They're mass nouns. BFO only contains count nouns. This is just a rule to avoid error. Now, material entity is a camera. And there are three kinds of material entity distinguished by BFO. This does not mean that BFO claims that these are the only three kinds of material entity. Indeed, it may very well be that system is a fourth kind of material entity. That's something that we have not yet reached the point of deciding. But these three are clear. So this is an object. It's a cow. And inside this object, we can distinguish various fiat object parts, which are distinguished by the fact that some of them taste better. And these are not limbs, or they're not separable. You can't take them out of the cow as they are, because as they are connected to all the other parts. So they're called fiat parts because they are divided up by fiat rather than by cutting, by physics. But then we have object aggregate. So this is an aggregate of 3 apples. That's an aggregate of 4 beetles. And the very same aggregate can gain and lose parts. So it could have been that there might have been a 5th beetle, or it could have been that there were only 3 beetles, but it was still the same aggregate. It was still the beetle. And this is an example of a very big and constantly changing object aggregate. You can think of an ontology as a catalog. It tells you what the kinds of things are in your warehouse. And an inventory tells you which instances of those kinds are in your warehouse. How many? All right, now we'll get to EMMO. So you'll recognize a family resemblance between this ontology. In fact, this is the very same ontology that you have on your handout, just going from left to right rather than from top to bottom. So they just imported BFO, and they took that structure as the basis for their materials modeling ontology. So you can see in more detail what you can see on your sheet. And then they say, since materials are perceived at different scales, the material entities should be subcategorized to cover all granularity levels so that the same material can be represented. You see they use a mass noun here. You have to say portion of material can be represented in EMMO or EMMO as a black box. In other words, just as one lump where you don't see any inside, or as a collection of subparts at different levels of granularity. So a molecule can be seen as a single rigid body, or it can be seen as a collection of atoms. They have 2 different levels of granularity. And now we go through all the levels of granularity. For some reason, they like Iron Maiden. So object aggregates are collections having as parts only objects. That's exactly what BFO says. But then there are objects, some of which are artifacts, some of which are organic, and some of which are natural aggregates or natural connected whole. And so and we don't need to bother about that. They distinguish 3 kinds of causal unity. Causal unity through engineered assembly, causal unity through internal physical forces, and as in the case of a molecule, and causal unity through a physical covering. And this is actually BFO also. BFO distinguishes these 3 kinds of objects. But then they don't think this is good enough. So they want, for instance, where do liquids go? A pool of water is not an object. If an object requires a causal unity on this list, it's not a fiat object part, and it's not an object aggregate. Although there may be an object aggregate when you look at it at the level of molecules. But the pool of liquid itself, as a black box, as it were, doesn't fit into BFO. And that is a real problem. And this problem is even worse if we think of a body of gas. So they want to represent all of these levels of granularity, and they want to do it in such a way that they can deal not just with solid objects, but also with liquid and gaseous objects or entities material entities and with plasma also. Moreover, they want to do justice to the fact that there are different kinds of models of these different kinds of entities. So there are electronic models, atomistic models, mesoscopic models based on the behavior of what in the modeling community are called beads, and then continuum models, which use differential equations basically. So the way they do this is BFL has material entity and then it has objects. And they say now, let's have material objects. And this blue part is in the realm of model. There are material objects which include subatomic objects, atomistic objects, mesoscopic objects, and continuum objects. And by material now, they mean just raw material. And then there are engineered objects. And a piece of engineered material is an engineered object. A component in a larger engineered object is an engineered object. And a system, here we get system. A system is an engineered object. And the system is something like the hydraulic system in your car. And now what they say is that, I don't know, I think that's probably a slide. So that's a bigger view, and that's another view. And I think their idea is that the key to understanding systems is down here. So they view the problem of what is a system in terms of how are portions of material organized, where the systems engineering view of systems is much more interested in the stuff over there, engineered objects, and more complicated things involving engineered objects as parts. So we don't need this, we don't need this. So this is how they begin to deal with liquids. So they distinguish two kinds of continuum object. On the one hand, there are solid continuum objects, which include crystals, polycrystals, amorphous solids. And then there are fluid continuum objects, which are portions of gas, portions of liquid, of forms. So that's, but for that, in the engineered objects could be a fluid too. They need to know that. At the moment, they officially, terminologically, do not know that. In their heart, they probably know it. I'll write that down. Any other questions while actually I should repeat it. So John just made the point that a fluid could be an engineered object too. And a gas, I guess.
Can you go back to the definition of object? My reasoning is saying that system implies bigger than object in my mind, just my intuition. I'm wondering, thought this.
Yeah. So, but the question is, must a system be bigger than an object, or could a system be an object? And at the CERC precursor event, we spent most of the afternoon addressing exactly that question. So supposing Siemens introduces a new line of washing machines called the Super AI-driven wash system. So they were selling systems, not just machines. But the system it came in a box and it was plugged into the wall. So could a machine, single object, be a system? I do not know. My intuitions agree with your intuitions, namely a system has to be something bigger than an object. However, even if the system is bigger than an object, it might still be an object aggregate. The hydraulic system you could see as a object aggregate. I don't know. This is something that I wish I could make progress. So if the system is bigger than an object, then it may be that we need to replace object aggregate by some term bigger than an object material entity, and then have object aggregates be one child term and system be another child term. But I would imagine that there are also going to be different kinds of systems. We might still need the single word system, but then more children. We'll do some work towards answering some of these questions in the afternoon. Okay, so let's go back to EMMO. All right, that's the end of EMMO. Now, I guess I am on to part 3. So let's go back to let's pause for questions. One bit. Yeah, that's on. We'll get it going out.
So it was interesting to hear you say you weren't sure. So is there a methodology that you're using to derive these ontologies? How do you know when you're sure? Like, is there a process that you use to build an ontology that you're checking? That do you know what I'm saying?
So there are various dimensions to the methodological question when it comes to ontology building, just as there are various dimensions to what I still think is an analogous question, namely, how do you build a scientific theory? And OWL provides tools which provide a framework which force certain methodological choice and which help you to make sure you're being methodologically correct, because the reasoners that come with Protégé, for instance, enable you to check your work to a certain. I think, and it seems that a lot of people agree with me, that being forced to use BFO brings a methodological railway line system, which is useful to build ontologies in a coherent way. So BFO doesn't just make people build ontologies in the same way, but it also helps people to build ontology. And the way it does that is by forcing you to make certain choices. So you have to decide, well, is this entity an object, or is it a fiat object part, or is it an object aggregate, or is it none of those things?
And then how do you do that?
So each of these terms has at least an elucidation. That is to say, you are told, first of all, a list of examples. You're given a list of examples of use of the term in context. And you're given some features which instances of the term or have. So you're given some necessary conditions of being an object. We don't, in every case, give you sufficient conditions, which is what you would need to have a real definition. And that's because we're working at the very top. And at the very top, you can't give definitions because there is nothing to start the definition going. There's no parent. Now there are people who try to create SOP, standard operating procedures for building ontology. And there is a website called military-ontology.org, which already has some links to such SOPs, but which will have much more in course of time. So the person who runs that website has created a big SOP system for the militaries.
And does that return a BFO standard ontology if you use it?
So one standard operating procedure is that you import BFO into Protégé, and then you build downwards from BFO. And that means that your starting point then is shared with a lot of other people, which is a good thing, because then you can compare what you decide to do next with what other people have already decided to do next.
It would seem to me.
Use my.
It would seem to me that I think I've had this discussion with you along the way about testing ontologies, and it would seem that I can envision two frameworks of testing. One is ontology for an board, and it probably is the standards or something like that. Also a notion of sort of failure of intended coverage.
Yep.
You tended to have the coverage you hoped for. Would you create a test that could prove it?
Yep.
Idea. But so I think, so that these ideas, I mean, I think ontology as it becomes an engineering practice, let's say, we'll need to think about.
So I'll take the second one first because I think that's the easiest one to deal with. Every ontology will manifest failure of coverage because every interesting ontology in a rich domain like material science spins is always going to be partial, because we're always going to be discovering new attributes of material, new ways of combining materials, and so the ontology will continually grow, just as the gene ontology can continually grow. So I don't think that's a real test. That's just the original sin. If someone claims to have a complete ontology, they are either not understanding what the problems are, or they are wrong. Now, with regard to the first question, there are people, including people in the army, in the military, who are doing these tests. So they have groups of database information systems which are not interoperable, and they build an ontology in order to advance interoperability between the two systems, and they test the degree to which interoperability is achieved. And therefore, we know one particular person who's doing this with BFO and comparing it with other alternative and top-level ontology. And he has become an advocate in BFO because he claims that when he runs his tests, BFO works better. And there are different reasons for that. So BFO is the most well-studied, it's the most well-documented ontology. It's easiest, therefore, facing according to it. There's always a human factor. I could never run such tests in an unbiased way.
Testability was something you sort of run when ring of LMI. And you said English is the basis for BFO.
There is already a Portuguese translation and a Chinese translation. In fact, the book is here in Chinese. So I don't mind Portuguese and Chinese.
All right. So then my question is there a cultural limitation to building ontologies, in that do other cultures, or have you run into anything where a culture might literally conceptually believe that something it's different than that?
Yeah.
And then how would you resolve that?
So I did face this problem. So the Chinese translators came to me with certain terms which they claimed could not be translated as Chinese. But I was able to talk them through it, and they discovered that there was a way of formulating all of the terms in Vietnam to China.
Do you believe, though, that there are any cultural limitations to building ontologies?
And the answer is no. I'm just trying to think of the reason. Let's suppose that we had a culture which had some kind of an institution or emotion or behavior pattern or habit or whatever it might be that was completely unknown to the English language. Then there would have to be some definition of that turf. And I believe that the experience shows that you can always provide some sort of definition. You may not get all the way, but you can at least find some place where it would go underneath already defined English terms. I don't know of any exception to that. And if you imagine what the exception would have to be, it would have to be something very mystical, something which was almost incoherent when you tried to express it in English. And I don't think that anyone would dare to be so rude to somebody who claimed to have an entity that was not capturable in English, but which was still coherent.